Thank you so much, you guys, for being here. And yes, our talk is titled Enlightenment, Tracing Light from the Computers to the Cosmos, and it's all about light. Um, so before we get into the meat of our talks, I wanted to introduce our speakers very briefly. So our first speaker is Jordan Smurgy, and he's in the computer science department at Yale. And his research involves theoretical computer science. And his fun fact is that he collects old US money. Our second speaker of today is Sumit Chaturvedi, and he's in the Department of Computer Science as well. And his research involves computer graphics. And his fun fact is that he loves to play football. And last but not least, we have Kostav Mitra, and he's in the astronomy department, and his research involves galaxy formation. And his fun fact is that he loves long walks and bike rides. So, I would like you to I would like to introduce you to the topic of light and how it interacts with materials and objects in many different ways. And so briefly, I would like to show you that light can be absorbed or be taken in. And an example of this around us every day is plants taking in or absorbing light energy to photosynthesize. Light can also be emitted or given off. And an example of this is the sun giving off a lot of light rays. And then another thing is that it can be passed through objects or materials, such as this, and we'll see this in a little bit in our second talk of today. Light can also bounce off of objects, and this is the case with, for example, mirrors, where as soon as light bounces off, you get a reflection and you can see yourself in the mirror. And then last but not least, light can bend or refract. And this is an example of a magnifying lens. And our first speaker of today, Jordan Smurgy, will actually go into details about this. So our first talk revolves around lenses and how we can understand how lenses work by just understanding that light is the universal speed limit. Our second topic is revolving around ray tracing and how we can look at light bending in different ways to essentially get amazing movies and animations. And last but not least, we have gravitational lensing, essentially tracing light rays on a cosmic scale to understand and measure the mass of a black hole. So with that, I would like to pass it on to Jordan, who will start us off with lenses.
Great. Thank you very much. So, as Brumi said, our first presentation will be about how we can understand focusing lenses. So, light is really a fascinating topic that humans have been studying and asking questions about and in some ways using for hundreds, even thousands of years. And I'd like to even just propose a very simple use of light as a tool by using light to tell time. Very simple sundials allow you to use the position of the sun to cast a shadow onto a dial and to use that as a fairly decent form of timekeeping. But there's much more complex ways in which we can understand and actually interact with light. So you may think to yourself, if you've used any one of the following, a magnifying glass, eyeglasses, or kind of in a rhetorical question, your eyes themselves. Because actually all of these rely on interacting with light in a very different way. And they actually all rely on this idea of having a focusing lens. And I'll show you a little bit more about how each of these work. So what do these focusing lenses actually do? So we talked about emission of light and we talked about many other properties, but focusing lenses actually don't do anything in terms of making new light or emitting light. They're really more about changing the direction of light, as you can kind of see in the graphic on the right. We have these sun beams kind of coming into the lens itself, but then they're being focused in a very specific way. And you may have used this before to say start a fire or heat up some water or something like that. But why are we even trying to do this? I mean, the focusing, the magnifying glass heating up something is a very practical use, but there are, in fact, much more important ways in which we can use this. For example, taking a blurry image like this, which would exist in the world around us, and bringing it into a crisp, sharp focus. Again, our eyes very fundamentally rely on having a focusing lens in the front part of our eye, and I'll show you a picture of that later. But this is a very fundamental motivation of why focusing lenses are very important. Without them, we really wouldn't be able to see anything, certainly not in any detail. So I just like to phrase the puzzle that we're trying to solve here as something like the following. So we have kind of this spread out or scattered light, if you will, coming in on the left. And on its own, it would just sort of produce this spread out blurry image on the right, or these spread out rays. And what we're really trying to do is use some sort of lens and bring them to a focus, which is basically a point where they will all come together. And I'll show you multiple examples of this, but you can think of this as the point that would be getting really hot if you used a magnifying glass to, say, start a small fire, or the point where your glasses or your eyes are focusing light so you can see. And this is really the puzzle we're trying to solve in order to understand a focusing lens, is how we can actually do this. So before we get started, we have to back up a little bit. And someone that you'll be hearing a lot about today is a fellow you may have heard of named Albert Einstein. And when I say we've been thinking about studying light for a long time, we've been thinking about this for thousands of years. And even Einstein, only about 100 years ago, kind of made some more fairly significant contributions to our understanding. And one thing that he helped us understand is that light can be thought of as a universal speed limit. And what that means is nothing can travel faster than it. And we can think of it as sort of bounding how quickly something can move. But it's a little bit more complicated than that. And so just saying that it's a speed limit isn't quite enough. So we need to dig into that a little bit more about what it means for light to be a speed limit. First of all, I'd like to visualize how fast light is. That number on the previous slide is maybe not so easy to visualize, but this is actually a little animation of light traveling from the Earth all the way to the moon and back. So you may have heard that when the astronauts flew to the moon in the 1960s on the Apollo missions, it took them about 4 days to get to the moon. Light takes about 1.2 seconds to get to the moon, so light is absurdly fast. And again, I think this visualization is a very concrete way of seeing just how fast light is. But a very important thing about this is that it does have a speed. Hundreds of years ago, we actually didn't know. Maybe light travels instantaneously. Maybe it travels slowly. Is very hard to know. But now we actually do understand the speed that light travels, and it's this 186,000 miles per second, 300 million meters per second, whatever number you prefer. But it's very quick. But something interesting is that just because light is the speed limit and we know how fast it travels, it doesn't mean that the speed itself can't change. Just like your car might have a top speed, but it may have to respect the speed limit on a particular road. Light actually will travel or propagate at different speeds in different materials. So for example, light travels in space at a different speed than it travels down on Earth in air. And that travels also at a different speed than it does in glass. So these numbers, again, are very hard to visualize, but I mainly put them for us to see that light does, in fact, travel quite a bit slower in glass than it does in air. For example, the difference is about 50%, so 120,000 miles per second versus 180,000 miles per second. Again, both are incredibly fast, but definitely it is traveling at different speeds and different materials. So even though it is the speed limit, its speed can actually change. It just means that nothing can travel faster than it in that material. And again, maybe another way to visualize this is with the car example. You have the car on the bottom traveling very quickly on maybe a highway versus a car traveling above. Maybe it has to contend with construction or traffic lights or something else. And ultimately, they'll travel at very different speeds. And light does something similar depending on the material that it's traveling through. So in a related note, I'd like to think about how we can actually determine the shortest path between 2 points. So I start with a very trivial example. It's exactly what you might be thinking, which is just a straight line. That is the shortest path between 2 points. Nothing too crazy there. But we actually have a slightly more complex question to answer when it comes to light, because we have to think about not just the shortest path, but we have to think about what is actually the fastest path. And the shortest and fastest paths are simple straight lines when we only have one material that we travel one speed in. But as soon as we start thinking about our analogy with the different roads, it actually is possible to travel further, but to do so more quickly. So for example, I'd like to play this animation where the top car actually travels more quickly for a lot of its journey, so that when it has to travel more slowly on this shorter portion, it actually makes it much more quickly. So I'd invite you to think about why that is the case. But the key takeaway here is that the fastest path and the shortest path can actually be different. And this was a very concrete example of where that happened. Basically, the top car was able to travel more quickly, and so was able to make up the distance that it had to travel. And this will become very fundamental in a second, but we just have to queue up this basic idea. So you might be thinking, well, maybe it's just better to always travel faster. So is it always better to just travel as fast as possible? Well, faster speed isn't always better, right? So here we see the car. The car on the green path does travel more quickly, but it has to travel so much more distance that it actually ends up being both a longer distance and a slower path. So now we found a path where the fastest and shortest path are back to the straight line path. And really the reason to discuss all of this is to think about this very interesting case that happens somewhere in the middle, where in fact, the top car travels more distance, but actually arrives at exactly the same time. And the very interesting thing we've done here is we've created a shortest, we can still look at the shortest path. It's always the straight line. The shortest path never changes. But we've now created two different paths of different distances, but equal time. And that's actually maybe not such a trivial observation initially. So we have the speed varying and the distances varying, but now we've created two different paths that actually are of equal time. And this is actually a very interesting observation that we can do because of traveling at different speeds. So I'd like to back up a second and think about what Einstein was really telling us. So yes, he was telling us that the speed of light in a vacuum is the fastest speed that anything can travel, the vacuum of space. But there's something more fundamental than that. What it really means to be the speed limit is to take the fastest path. Because if you didn't take the fastest path, then you're not really being the speed limit. You sort of have to be able to get from point A to point B as quickly as possible. And if something else that could travel more slowly could take a different path and get there before you, then you're not really being the speed limit. So really the fundamental takeaway I want to propose from what Einstein was trying to tell us is that light is traveling on paths that we can think of as the fastest paths. And there's a very interesting consequence of thinking about it in this way. So I'd like to try to apply this example that we've just done and see if we can use it towards our attempts to make a focusing lens. So if I just sort of take this rectangular shape here, maybe you can just think of it as kind of like the pane of glass on a window. We want to see if it will actually get us this convergence of light that we've been looking for. And unfortunately, this doesn't quite work. So I'd like to play an animation of light sort of traveling in from the left. You can see it slows down. I'll play it one more time. You can see the light travels faster. It slows down when it goes through the glass, and it travels faster on the other side. But everything kind of came in a very symmetrical way. All the light rays were sort of parallel to each other, and then they came out in exactly that same structure. So it didn't quite do what we were looking for, but it's a good start. But again, the key insight we're trying to leverage here is that light is taking the fastest path. And so the reason our example didn't work is our fastest paths were all in straight lines, and our fastest paths were sort of all over the place, and so it didn't really do anything for us. But remember, the shortest path is not always the fastest path. And so now instead of using the two different roads for the car, we want to think about air and glass, which remember light travels at different speeds in, namely light travels faster in air than it travels in glass. And so we might be able to set up something similar to our car example where we could actually make two different paths that were both the same length of time, meaning that we could actually get the light to come from multiple paths and converge at a point, which is exactly what we're looking for. But maybe we should pause for a moment and ask, like, can light actually bend like this? Again, this maybe seems not so trivial. So again, continuing with my car analogy, I'd like to propose just thinking about what would happen if a car was driving on a road, and then suddenly just the tires on the right side of the car got into some mud. So basically the muddy tires kind of slowed down while the rest of the car traveled at the same speed. What do you think might happen? And so I've just done kind of a small animation, but it might be something like the following, where because the car experiences that mud just on one side, it actually kind of pulls the car in that direction. And you actually see our familiar shape of a bent path. So definitely skipping a lot of details that we don't have time to get into today that maybe we can discuss in the Q&A, but light is actually able to take these bent paths for a somewhat analogous reason. It's not a perfect analogy, but basically the fact that light travels at two different speeds in these materials, if it enters at an angle, it will also experience this kind of asymmetrical force where it slows down a bit more on one side than another. And again, it's not a perfect analogy, but you'll actually observe this bent shape when light travels between two different materials. So light can actually take these bent paths too. So now to bring our whole puzzle together here, what we really need to do is figure out how to make many different paths all sort of appear like they're the fastest path. And if we can sort of trick light into taking all these fastest paths, we might actually be able to bring a lot of light to a point. And that's actually exactly our problem statement for a focusing lens. So let's see if we can pull that off. So I'd like to go back to our original example and see where it sort of broke down. So when we just had one light ray traveling through the middle, this is actually okay. We brought our light from the left to the right, and we stayed on target for our focused point. But it's actually when we start bringing in more light that we have a problem, because now, as we bring in these multiple rays, now all of a sudden they're not converging to our point anymore. So this is where our example kind of broke down. So how can we change this using the pieces that we've built? So the key idea is that maybe we can actually change the shape a little bit, and we can start trying to change these paths. And the key idea will be to let the light that travels sort of further up, so those kind of first and third rays in the picture, they have to travel more distance to reach our point. So in order to try to get them there at the same time, maybe we can let them travel through the glass a little bit less, and then maybe they'll arrive more quickly. So let's try that. So due to this bent shape, they will actually travel a bit less through the glass. And because of that shape, they'll actually bend just a little bit. And this was close, but we didn't quite get a convergent, but this is on the right track. We almost have it. So if we actually just make this shape a little bit more exaggerated, where again, these first and third rays will travel a little bit through a little bit less glass, where light travels more slowly, and they'll travel through a little bit more air, where it travels more quickly. We can actually build these exact bent shapes that we were talking about earlier. And as the light travels more slowly and comes out, it will actually bend and bring itself beautifully to a focal point. So I'd like to bring this all together in one final example here. Watch all the light come in, slow down, exit, bend, and converge to a point exactly as we hoped. And really, the key idea for doing this is that all of these paths now become paths of the same amount of time. So they are not paths of the same distance. The shortest path is still the center path, but they can all become paths of equal time. And because of light's ability to bend when it changes going through materials, all the paths of the same time will converge to a point, which is exactly what we were looking for. So I'd like to end by talking about why this is useful. So this is actually exactly how the focusing lens in our eye works. So light comes in, just like the pictures we've been seeing. It goes through the focusing lens there at the front of our eye, and it focuses onto the back of our eye in a light-sensitive part called the retina. That's visually where we actually see an image. And you may have heard of the terms nearsighted or farsighted before. And basically what that corresponds to is the light coming into the lens and being focused either a little bit in front of or a little bit behind the retina. And that leads to these blurry images like you see here. Actually, exactly when the light is focused precisely on the back of our eye is when we can see a clear, crisp image. And so if we are a little bit nearsighted or a little bit farsighted, we can actually use eyeglasses to just bend the light slightly differently and allow it to focus on the back of our eye exactly like we hoped. So I hope that gives you a little bit of an insight into how we can visualize how a focusing lens works, simply by knowing that light is the universal speed limit and it travels at different speeds. I hope that gives you some insight into how we can design a focusing lens and really using no math or physics. Hopefully this gives you actually a pretty strong intuition about how these focusing lenses actually work. And with that, I'd like to queue up Sumit's next talk, which is going to introduce ray tracing, because we've observed all these cool properties of light in real life, but it's actually very cool and very insightful to figure out how to model it in a digital space. And that's exactly what we will be doing in the next talk.
Hi, I'm Sumit. I'm a first-year computer science student, and I'm going to build on the ideas that Jordan presented and discuss ray tracing. And the key idea that I want to leave you with is that this is really a way to paint digitally with light. So imagine it's 2050, and of course, like ChatGPT and all these things are making immense progress. But now the tech overlords have said that we have to spend the rest of our lives in virtual worlds. And this is because they want to train embodied super intelligent agents based on our behavior. So given that this is definitely going to happen, which world would you rather live in? The one on the left or the one on the right? Notice that in the picture on the left, you have clear, crisp water, nice texture in trees and grass, and clouds in the sky. All of these are absent in the picture on the right. And this is because the picture on the left is created using exactly the technique that I'm going to discuss, ray tracing. So my preference will definitely be this. Now note that this technique has already been widely adopted in a lot of areas such as video games, virtual try-ons, virtual worlds, and of course, virtual reality. So now the question is, how do we get here? And the key insight here is that the appearance of these different materials depends on the microscopic interaction between light and matter. So here I have 5 materials: mirror, metal, ceramic, glass, and the reflecting patch on a safety vest. All of them look very different, and it all has to do with how light interacts with the material surface at a microscopic level. This is what we are going to discuss next. So mirror is the easiest to understand. It doesn't have any color of its own, as Brahmi told us. Any incoming light is reflected in one direction. Metal is a bit different. When light hits the metal surface, it splits into a bunch of beams and goes in an outgoing direction. This is why often metal looks like a shiny, blurry mirror. Now, ceramic is different from both of these. When light hits ceramic, it reflects in all directions. So that is why you see a sort of homogeneous color in the spot. Now, from Jordan's talk, we know that not all materials reflect light. Some of them allow light to go through, and glass is one such material. When light passes through glass, it bends in towards the normal. Lastly, we have esoteric materials such as the reflecting patch on a safety vest. So the fascinating thing about this material is that it sends light back in the direction it came from. And this is why when you shine a light on this material at night, it serves its purpose and can see the person who's wearing this clearly. In summary, the microscopic interaction between light and the surface of all these materials influences the final appearance that we see. And this is crucial when we are trying to do ray tracing. Now, the good thing is that we are not confined to materials that are present in nature. When we are using these digitally, we can make up our own materials. And this is very crucial for doing art and in movies as well. So for example, here I'm artificially manipulating the properties of this material to make it more shiny. And maybe you can agree that in doing so, it starts to look a bit more like metal. Here I'm doing the same, just that I'm making it more like ceramic or pot. Now, one crucial thing that we need to understand is that the color that we see depends on the angles at which light hits the surface and the angle at which it comes into our eyes. So here I have this very special fabric called silk shot, and hopefully you can see this pattern where at some places it looks blue and at other places it looks red. And this is all to do with the angle at which light is hitting the surface and the angle at which it's coming into our eyes. So for example, if light is arranged as so, we see, one second, a bluish color. And if it's like so, we see red. And why is this important? So this is important because it plays a role in shading. So when we see this spot, we think of it in 3D, and this is because of the angles at which light is hitting the spot. So for example, here we see a lighter orange. That may be because light is coming and hitting it and coming into our eyes like this. And somewhere here, we see a darker color. So now we are almost there to understand ray tracing. And as a motivating example, let's first understand how ray tracing occurs in nature, or in other words, how do we actually see things? So let's say I'm standing here and I'm looking at the patch of grass in front of me. What is happening when I actually see the grass? Well, light rays travel all the way from the sun, hit this patch of grass, reflect, and some of the rays come into our eyes. But this is not the only way in which light travels. Light, in fact, takes many paths. So, for example, it can hit a nearby patch of grass, reflect, again reflect, and come into our eyes. And the key idea that I want to transmit over here is that light transports color. So for example, again, going through this illustration, let's say the ray hit the sky first. It will pick up some blue color, deposit it on the next surface it hits, which is this mountain, pick up the color of the mountain, deposit it on the patch of grass, And finally, the culmination of all these colors will enter our eye. So in this way, light is really like a paintbrush, and it's painting the picture that we see in our eyes. So now we are almost ready to describe how ray tracing happens digitally. And as a motivating example, we'll take a look at how to ray trace this dinosaur. Now, one key question which I haven't spoken about so far is how to represent these objects digitally. So here I have a 3D modeling tool called Blender, and this is widely used by commercial artists to make scenes. And here a light source is simply represented by a point in 3D space. Similarly, a camera is a 2D plane. Now, the most complicated part of the scene is the dino. And this is represented by a bunch of triangles that have been stitched together. So here I show you a close-up of the dino where you can clearly see the triangles that are stitched together. And with each triangle here, we associate the color of the dino and the reflecting properties, in that how, when light ray hits this triangle, how will it bounce? So now we are ready to describe how ray tracing happens digitally. So from our light source, we'll cast a bunch of rays into the scene. Some of the rays will hit the dino. They'll reflect and deposit some green color on our camera. And this will happen again. And if we keep doing this carefully over and over again, then a rough image of the dino will start forming on our camera. And if we do it in high enough resolution, we'll see the full dinosaur. Now, one key thing that is missing in this description, which many of you might be wondering about, is how do we see shadows? So the key idea is to count the number of light sources that are reaching a point and multiply the color by that. So for example, let's say I have 2 light sources. And let's say I want to compute the color at this point. So since both of the light sources can reach this point, I will simply multiply the color by 2 by 2, since both of them can reach it. And now, if I have a region in a shadow, then the first light source can reach it, but the second one is occluded or blocked by the tail. And so I will multiply the color by half. And in doing so, that portion will start to look a bit dimmer. And that is how you get shadows. Now, all this requires, as you can imagine, a lot of compute. And over the years, specialized hardware by companies such as NVIDIA have come up, known as GPUs or graphical processing units, that allow you to do this very fast. And now even in real time. But even so, this is very expensive in practice. And like commercial movie houses such as Pixar and so on have to employ thousands of these GPUs, all casting rays into a scene, all computing colors over and over again. So a key question is, how do we make ray tracing faster? And this is indeed an active area of research. And I would just like to give you one interesting way in which we can do so. So note that the flaw with our current approach is that when we cast rays into the scene, many of them won't make their way to our camera. Now, this can be avoided by doing ray tracing in reverse. So instead of tracing rays from the light source, let's start from a camera, cast rays from the camera, and then go back. And in this way, we can reduce the number of computation by at least 3 orders of magnitude, making it much faster. And this is one render that I made for a class project a while back. So as you can see, the rays of light are going into the house, and you can see shadows and so on. And if you do this properly, you can do interesting things like smoke and all that good stuff as well. Hopefully you guys can see like there's some smoke coming out of the chimneys and so on. So hopefully I've convinced you that even though ray tracing is very expensive, it is worth it because we can make amazing art, movies, and games. And now I would like to hand it over to Kostov, who will talk about ray tracing at a cosmological scale. Thank you.
Hello, everyone. Thank you, Sumit, for handing over the baton. So Jordan talked about how lenses can bend the path of light, and then Sumit talked about tracing light digitally to create fantastic artwork that goes into movie and games and everything. Now, I'll have both of these aspects in my talk, but in a completely astrophysical cosmological context. I'll talk about how light gets bent and curved by something called gravitational lens, and how we can trace that bent or curved path of light to measure mass of exotic astrophysical objects called black holes. So the title of my talk is Tracing Light Through the Cosmos. But first, I'll draw your attention to this beautiful photograph taken this year, just a month or so ago, of the total solar eclipse. I hope some of you at least traveled to see the spectacle of the total solar eclipse. And even if you didn't travel, at least hopefully you got a pair of safety glasses and got to see this partial eclipse. So this view mesmerized millions of people just about a month ago. I'll start my story with a similar photograph of a total solar eclipse that happened more than 100 years ago. This photograph revolutionized the field of physics. Then I'll end my talk with another spectacular photograph taken exactly 100 years later in 2019 that made headlines all over the world. I'm sure many of you saw this blurry image 5 years ago, and this was in 2019. So we'll end our story with how we can use this image to precisely measure mass of black holes. Now, the 1919 photograph of the eclipse was taken by a British astronomer, Arthur Eddington. You might not know this person, but you definitely know the other person in this photograph sitting beside him. So this is Albert Einstein, and it's Eddington's observations during the 1919 eclipse that actually made Einstein a global celebrity. So these will be the two main characters in our story. And our story will mainly revolve around the central question, what is gravity? We'll talk about how light gets affected by gravity and how we can use that light to measure extreme examples of gravity. But first, whenever we talk about gravity, this name and this person pops in our mind. Sir Isaac Newton in 1600s came up with the universal law of gravitation, which says that every single object in the universe attracts every other object with a simple force. That force is just a multiplication of the masses of these two objects, and it goes down as the two objects go far apart from each other. So it's inversely proportional to the distance. Now, this equation, which is actually surprisingly simple equation, could explain everything from falling apples to motion of baseball to motion of heavenly objects like moons and planets. So Newton's theory was so successful that it prevailed for more than 200 years until this patent office clerk in early 1900s realized that Newton's theory of gravity must be wrong. It is inconsistent with the speed of light being the speed limit of information. Now, Jordan talked about this speed limit, and Einstein came up with this idea that there is a speed limit in the universe, and it is the speed of light. And Newton's idea of gravity doesn't really fit into this picture because gravity acts instantly. The gravitational force, as Newton described it, between the sun and the moon, or the sun and the earth, or the earth and the moon, they act instantly. But as Jordan showed, light is really fast, but it takes some amount of time to go between the earth and the moon. So gravity, that force, is violating the speed limit, and that cannot happen. So Einstein dwelled on this puzzle for about a decade, and finally, around 1915, he came up with his own theory of gravity. Now, it was a really mathematically difficult and bizarre theory. Einstein actually had to learn a new branch of mathematics to fully explain his ideas. But the basic idea is this: gravity is a manifestation of bending of space and distortion of time around every object in the universe. So imagine this. Imagine space being an extended, stretched rubber sheet. Now, if you place a heavy object on that rubber sheet, it's going to bend that sheet around it. Now, that bending is proportional to how heavy that object is. And if you roll a smaller object in that bent rubber sheet, its path will be curved. And that's exactly what's happening in the real world. Objects are bending space around it, and when smaller objects move in that curved space, their paths also get bent. So Einstein basically replaced this Newtonian idea of a gravitational force with the idea that parts of these objects are bending because space-time is curved around Earth thanks to its mass. Now, it's a really bizarre theory, and the equation looks really horrible. The left-hand side of this equation explains that bending of space and time. The right-hand side of the equation tells how it depends on the amount of mass in its vicinity. But this equation was really buried in 1915-16 when Einstein came up with it. No one really knew about it, and it was the time of the First World War. So Europe was divided, and Einstein was starving in Berlin, but somehow a letter reached Cambridge through the neutral territory of Netherlands, and this equation reached the hands of Sir Arthur Eddington. Now, Eddington was a physicist. He was the professor at Cambridge University, and he understood the true significance of this equation. He realized that what it means is that since gravity is a bending of space and time, then light itself shouldn't be exempt from its effects. In Newton's picture, when gravity was just a force between objects, then light had no role to play in that whole picture. Light didn't have mass, so it was not affected by Newton's idea of gravity. But if gravity is the bending of space itself, then light paths should also get bent. So Eddington realized that light from distant stars, as it moves very close to our sun, should be curved, should be bent, and this is an effect which should be observable. So this is kind of similar to bending of light that Jordan talked about using a lens, but this time light is being bent by gravity. So it's called gravitational lensing. Now, what does that look like? For example, if I had this image in front of you in a room, and I placed a really heavy object that is so heavy that it distorts space around it, then you would be able to see the effect of a gravitational lens. What would that look like? It's something like this. And if I move the object, then this is how the distortion of the background image should look like because of gravitational lensing. Now, sun is not that strong of a lens. It's a weak lens, but its effect should still be detectable. So Eddington realized that we can look at positions of stars when they're pretty close to the sun um, in the sky, and we can see the effect of these tiny distortions of the background images, in this case, the background positions of stars. So it's a simple thing to go and test, right? We can go out at night, point our telescope at some part of the sky, and note down the positions of stars. And then a few months later, when the sun is roughly in the same part of the sky, we can go out during daytime and note down the positions of those stars. The same stars, but this time their paths being distorted by the sun being present between them and us. So this distortion is really small, but it's something which is noticeable. Now we can zoom in and it will look something like this. The orange points here show the true positions of those stars, and the white points show the distorted positions. So why don't we just go ahead and do it? Well, the reason is this. You can't really observe positions of stars when the sun is up in the sky. It's too bright. Even if you block it out, the glare of the atmosphere is too bright. It's impossible to see any star. So what if we had some miraculous way of blocking out the sun even before its rays could enter the atmosphere? That would be the perfect setup for this experiment, right? Can we block the sun? Well, nature provides us with a golden opportunity. So this is the path of the eclipse that happened just a month ago. And Eddington saw a very similar opportunity in a 1919 solar eclipse that crossed South America and Africa. He teamed up with another astronomer, Frank Dyson, and they led two expeditions, one in South America and one in Africa. This was Eddington's setup in South America, and he took this spectacular photograph. And he noted the positions of the stars in that photograph. I'm zooming in on a part of the photograph here. He marked the positions of stars with a pen, and he carefully analyzed their positions with kind of a microscope-like instrument for the next few months, and he measured this angle. And the shift was exactly as Einstein had predicted. This was a huge victory for Einstein's theory of gravity. Eddington's observation during the eclipse proved it to be correct, and it made headlines all over the world. And that made Einstein famous overnight. Now, around the same time, physicists were also looking into other implications of Einstein's equation. As I said, it is a distortion of space that manifests itself as the effect of gravity. And the more compact the object is, the stronger the distortion of space will be. So for example, if we keep squeezing the sun, the entire mass of the sun, into smaller and smaller volume, then the bending of space around it will be stronger and stronger. There are actually objects in the universe which are very dense, more dense than the sun, and their gravitational effect around them are very strong. At some point, for example, if the entire mass of the sun is squeezed to less than a mile in size, then the bending of space is so strong that even light cannot escape from it. It's like poking a hole in this fabric of space. And that was the mathematical idea of black holes. Now, it took astrophysicists 100 years, about a century of astrophysical observations to realize that this mathematical idea of black hole is not just a mathematical idea, it really exists in nature. And we expect it to look something like this. Now, this is a photograph of a black hole from the movie Interstellar, which was actually produced by the same ray tracing techniques that Sumit talked about. But we don't have to rely on this photograph. We have a real photograph of a black hole. This was taken in 2019 by the Event Horizon Telescope, which is actually a collaboration of many radio telescopes spread all over the world. And what we are looking at here is actually the image of hot gas moving around a black hole in a very distant galaxy. So I'll show this movie where we are zooming in into a distant galaxy. And if we keep zooming in towards its center, the black hole lies over there. And there is really hot, energetic gas moving around it. And if we get very close to the black hole, then we can see that the light paths are actually bent. They are curved because of black hole's gravity. And that curved path, we can trace them digitally. And those light rays are being focused towards us to get this spectacular image that the radio telescopes observed. So this is the image that made headlines in all major newspapers at the time. And physicists can actually trace these light paths digitally to measure how they are bending and curving. And from that, we can measure the strength of the gravity around the black hole. The strength of the gravity is a direct reflection of the mass of the black hole. And we measure it to be an extremely massive black hole, actually. It's 6.5 billion times the mass of the sun. And we can measure it very precisely because of Einstein's theory of gravity and because how we can trace light in a curved space because of gravity. So we talked about light in different scenarios. Jordan talked about how lenses work by bending light because light travels with different speed in different medium. Sumit talked about how we can trace light digitally to create spectacular hyper-realistic images that go into games and movies. And I talked about how light bends because of the effect of gravity and how we can trace that to learn things about the universe. Thank you.